Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review what was covered in weeks 4 and 5. So we started by looking at percentage increase and decrease. We need to be able to take a quantity like $60 and increase or decrease it by a certain percentage. So if I want to increase $60 by 40%, well, notice that 100% of 60 is 60. So what we're really doing here is we're taking 100% of 60 and we're adding 40% of 60. So really, what we're doing is we're finding 140% of 60. And 140% of 60 is just 1.4 times 60, which is $84. What about if we wanted to decrease 60 by 40%? Well, here we're taking 60 or 100% of 60 and we're subtracting 40% of 60. So 100% minus 40% is 60%. So here we're just finding 60% of 60, which is just 0.6 times 60 or $36. So there is a quick way to do it. So to increase a quantity by R%, you multiply by 1 plus R over 100. So what's going on here? Well, when we wanted to increase 60 by 40%, we just added 40% to 100%, got 140%, and found that percent of 60. So that's what this formula is. 1 is the same as 100%. 40% is 40 over 100. That's what it's doing here. Now, when we decreased 60 by 40%, the only difference was instead of adding the 40%, we subtracted it. So when you're decreasing a quantity by R%, you times by 1 minus R over 100. So this is really important that we know this because this forms the basis for the exponential growth and decay formula. So when something has exponential growth, it increases at an increasing rate, and when it has exponential decay, it decreases at a decreasing rate. This is the formula for exponential growth and decay. A, the amount you have equals P times 1 plus or minus R over 100 to the power of N. P is the value you started with, R is the rate of increase or decrease as a percent, and N is the number of times you increase or decrease the amount. So what does this plus or minus here mean? Well, you use plus if you're increasing, you use minus if you're decreasing. So let's apply this to this question here. So the population of a town is 90,000. What will be the population in 20 years' time if it increases by 5% each year? So A, the amount is just the original number, which was 90,000. And what we're doing is increasing it by 5% 20 times each year for 20 years. So we multiply by 1 plus R. So R is 5%. So it's 5 over 100 to the power of 20 because there are 20 increases. Notice here I used a plus because it's increasing by 5% each year. So putting that in our calculator, we can put it in straight like that. We get about 238,797. So the population will have grown a lot in that time because it's increasing at an increasing rate. What exactly does that mean? Well, 5% of 90,000 is 4,500. So this town will increase by 4,500 people in the first year. In the second year, it will increase by a bit more. It might go up by like 5,000 in the second year. And then it'll increase by more in the third year, might go up by like 5,500, etc. So that's what I mean by increases at an increasing rate, and that's why it gets really big really quickly. Let's try this question. My car depreciates in value by 10% each year. So depreciates just means it loses value. It's losing 10% of its value each year. So it's now worth 15,000. What's its value 10 years ago? Well, we're going to use the same formula here, but this time we're not figuring out how much it will be worth in the future. We're figuring out how much it was worth in the past. So this time we already know A. A is the amount. It's now worth $15,000. What we want to do is find P. We want to find the initial value. What value did it start at so that when it loses 10% each year, it's now worth $15,000? So we're still using the same formula here, but this time, because the quantity is decreasing, it's going to be 1 minus r over 100. So r is 10, it's going to be 1 minus 10 over 100, and there were 10 decreases. So once a year for 10 years, so a 10 goes there. So I want to solve this for p to find the initial value. This might look like a complicated equation to solve, but it's actually pretty simple. 15,000 equals p times some number. This is just some number. We don't know off the top of our heads, but it's just a number. So p is just going to be 15,000 divided by this number. So putting this in our calculator, we get about $43,020. So that means the car started at this and we took 10% of this value away for 10 years. It's ended up at $15,000. So when you want to find the value of something or the amount of a quantity in the future, you times. When you want to find the original amount, you divide. Let's now look at compound interest. So compound interest is a type of exponential growth. It's the kind of interest that banks use. So because it's exponential growth, we're still going to use the exponential growth formula. So the only difference between this and what we did on the previous slide is that you must have R and N in the same units. So I'll explain what that means in a second. So let's try a compound interest question. I invest 8,000, 3% per annum. How much will I have in 6 years if interest is compounded annually? So this is straightforward. The amount you will have is just P, which is principal, the original amount, times 1 plus r over 100 to the power of 6. You can put that straight in your calculator, and to the nearest dollar you get about 9,552. Okay, so what about if interest wasn't compounded annually, but it's compounded monthly? Well, we just need to change our formula a bit. So it's still going to be A equals P 1 plus R over 100 to the power of N. But we have to make sure R and N are in the same units. So because it's compounded monthly, the number of increases is going to be way more. The number of times we've increased is going to be 12 times per year for 6 years. So there's actually 72 increases. N is 72. But because N is in months, R has to be in months. So 3% per annum per year means 3 over 12 or 0.25% per month. So what did I do here differently? Well, I divided 3 by 12 to get the rate, and I timesed N by 12 to get the number of increases. So we just had to change our formula slightly here because it wasn't compounded annually, it was compounded monthly. There are 72 months in 6 years, so we have to do the interest rate per month, not per year. 3 divided by 12 is 0.25. So putting that in our calculator, to the nearest dollar, we get 9,576. So we get slightly more if it's compounded monthly. So with compound interest, the more frequent the compound, the more money you end up having. All right, let's look at one more example. So if I invest $20,000 at 4% per annum, interest compounded annually, approximately how long will it take my investment to double? So I'm still going to use the same formula for compound interest. So here I'm told that it's 4% per annum, so I'm going to change R to 4, and we're told that the initial investment is $20,000. Now, I want the investment to double. So it started at $20,000. I want the amount it's now worth to be $40,000. So in this equation, I'm actually solving for N. Now, that's not easy. So what we want to do is try to get N by itself as much as we can. So what I can do is I can divide both sides of the equation by 20,000. So 40,000 divided 20,000 is just 2. So note that 1 plus 4 over 100 is 1.04. So now I've got to solve this equation. Now, we don't actually know how to solve equations where the unknown is in the power. So you just have to use trial and error for this. So all you can do is keep trying different values of N until 1.04 to the power of N gets you to 2. So it turns out the answer exactly is about 17.67. So N is approximately 18. What that means is you need about 18 years for the investment to double. If you substitute N for 18 here into this equation, you'll see the amount will be a little more than 40,000, so it will have doubled. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.